Question of all. What is everything really made of? You know, when you think about it, the first idea that pops into your head is probably these tiny, tiny specks, right? These indivisible point-like particles.
Mm.
And then you start wondering, okay, if it's really a point, like zero size, how does energy, maybe energy from all over the place, all corners of the universe, how does it all focus down onto that? Well, get ready, because that picture, we're going to take it apart. The reality that modern physics paints is much stranger, much more profound, and honestly, pretty mind-bending.
Absolutely. That's exactly our mission for this deep dive. We want to walk you through that journey, starting from that simple, almost intuitive idea of a point and see where physics had to go. We'll look at the contradictions that popped up and how they forced scientists to basically rethink reality itself, moving from, little billiard balls to something, well, something else entirely.
Okay, so let's start there. This point-like particle. In the standard model of particle physics, that's our best current description of all this fundamental stuff. They use that term point-like all the time. But what does it actually mean? Are physicists saying an electron is truly a zero-dimensional dot? Or is it more like a useful simplification?
It's definitely an idealization,
Yeah.
a mathematical abstraction. It's incredibly useful for calculations, treats these fundamental particles as having no size, no dimensions. And look, it's been amazingly successful. The predictions are just stunningly accurate. But we should be cautious, right? Remember, atom meant indivisible.
Right. Until we found protons, neutrons, electrons.
Exactly. So
Right.
point-like is sort of the current placeholder. It means, as far as we can tell, down to the limits of our experiments, it behaves as if it has no size. But it doesn't mean it definitively has zero size.
Okay, so who are these fundamental players currently treated as point-like in the standard model? Can you give us a quick rundown?
Sure. Right now, we have 17 recognized elementary particles. You can broadly group them. They're the fermions. These are the matter particles. Think electrons, the quarks that make up protons and neutrons, neutrinos.
The stuff things are made of.
Precisely. Then you have the bosons. These guys are generally the force carriers. The photon for electromagnetism, the W and Z for the weak force, gluons for the strong force that holds nuclei together.
Okay.
And then there's the superstar, the Higgs boson. It's in a class of its own, really. It's connected to the Higgs field, which is how particles get their mass. And yeah, all of these electrons, quarks, photons, Higgs are currently treated as point-like in the math.
What's fascinating, though, is that even if this point-like idea works great for calculations, it starts to crack, theoretically, when you bring in quantum mechanics. What happens if you try to apply Heisenberg's uncertainty principle to a perfect point particle?
Yeah, that's where you hit the first major wall. The uncertainty principle connects position and momentum. If you knew a particle's position perfectly, like it's exactly at this dimensionless point, zero uncertainty, then the principle demands its momentum must be infinitely uncertain.
Infinite momentum means infinite energy.
Exactly. E equals PC for massless things, roughly. And kinetic energy depends on momentum. Infinite momentum implies infinite energy. Yeah. And that's just, well, it's physically impossible. It doesn't make sense. Nature doesn't seem to do infinities like that. So the very idea of a perfect mathematical point clashes, fundamentally, with the quantum rules of the game.
And this leads into that whole wave-particle duality thing, doesn't it?
It does, directly.
Yeah.
Particles aren't just tiny dots. They're also waves. They're described by something called a wave function, which is basically a cloud of probability. Think about an electron in an atom. It's not orbiting like a planet. It exists as this probability cloud, occupying a definite, though tiny, volume, maybe around 10 to the minus 30 cubic meters for hydrogen.
So it takes up space. It's not a point.
Right. It's smeared out. The particle nature, the point-like aspect, really only shows up when you measure it, interact with it. Its wave-like nature is fundamental and just incompatible with being a zero-size point all the time.
Okay, this is where it gets really interesting, because this isn't just theorists scratching their heads. We've actually tried to measure the size of these things, right? Using particle colliders, like smashing things together at incredible speeds and seeing how they bounce off. Almost like finding something in a dark room by throwing baseballs at it.
That's a pretty good analogy, yeah. High-energy scattering experiments. We accelerate particles, like electrons, to near light speed and slam them into targets, or into each other. If the electron had some internal structure, some finite size, the way it scatters the angles and energies of the particles coming out would be different from what you'd expect for a perfect point.
And what have we found? For the electron, specifically.
Well, here's the kicker. So far, electrons show zero deviation from the point-like predictions. None.
Zero. So they are points.
Not quite. This is crucial. It doesn't prove they have zero size. It just sets an incredibly small upper limit on their size. We know that if the electron does have a size, it must be smaller than about 10 to the minus 18 meters. That's incredibly tiny.
Wow. Okay.
So for now, physicists tend to use Occam's razor. The simplest explanation that fits the data is that it's point-like. We assume it's a point until an experiment proves otherwise.
But even with that experimental agreement, there's another huge theoretical problem lurking, isn't there? The whole singularity issue. What happens if you try to pack, say, electric charge into a zero-volume point?
Exactly. This is where things really break down theoretically. In classical electromagnetism, if you have a point charge, the electric field right at the point becomes infinitely strong.
Infinite field, infinite energy again.
Infinite self-energy, yeah. The energy stored in the field associated with the charge itself blows up. And since EMC squared, that implies infinite mass for the particle, which is obviously wrong. Electrons have a tiny mass, not infinite.
So how do physicists deal with that in calculations?
We use a mathematical technique called renormalization. Yeah, it's pretty clever, but conceptually a bit weird. You essentially find ways to subtract these infinities from each other to get finite, sensible answers that match experiments incredibly well.
So it's like a mathematical patch.
You could sort of say that. It works brilliantly for making predictions, but it doesn't really solve the underlying conceptual problem of the infinity starting point. It tells us the point idea is probably flawed at a dim level.
And it gets worse with gravity, right? General relativity.
Oh yeah, much worse. In Einstein's theory, if you squeeze any mass or energy into a true mathematical point, zero volume, you inevitably create a gravitational singularity. Think the center of a black hole, or the very beginning of the Big Bang in the Standard Model. You get infinite density, infinite space-time curvature. The equations just break. They go haywire.
Which physicists generally think means the theory is incomplete there, not that reality is actually infinite.
Precisely. These singularities are mathematical signals that our current theories, classical electromagnetism, general relativity, even parts of quantum mechanics when combined naively, have reached their limits. The point-particle concept, pushed to its extreme, fundamentally breaks our descriptions of physics.
So faced with all these problems, infinite energies, the uncertainty principle clash, singularities physicists realized the point particle just wasn't cutting it. They needed a completely new foundation. And that led to quantum field theory, QFT.
That's the huge leap. QFT completely reframes the picture. Its core idea is mind-blowing. The fundamental stuff of the universe isn't particles at all. It's fields. Continuous fluid-like fields that permeate all of space and time. There's an electron field, a photon field, which is the electromagnetic field, a quark field, a Higgs field. Everything has its own field, everywhere.
Wow. So instead of tiny specks moving through empty space.
The space is the fields. It's full of these overlapping quantum fields. And this immediately solves old problems like action at a distance. How does one particle instantly know another is there?
Right.
In QFT, it doesn't. Influences travel as disturbances, as ripples, through the field, always at or below the speed of light, like dropping a pebble in a pond. The effect spreads outwards.
Okay, but wait. If fields are the fundamental reality, then what on earth is a particle? Because we definitely detect particles, like electrons and photons.
Great question. It's a shift in perspective. In QFT, a particle isn't a tiny object that has energy or sits in a field. A particle is a localized vibration, a ripple, a quantized excitation of its underlying field.
A ripple in the field?
Exactly. Think of the electromagnetic field just sitting there. If you wiggle it just right, with the right amount of energy, pop, a photon appears. That photon is the wiggle, the ripple. An electron is a localized ripple in the electron field.
Okay, that's elegant. And does that help explain things like particles being created or destroyed, like in the LHC?
Perfectly. That used to be really puzzling. How can you smash two protons together and get a shower of completely different particles? In QFT, it's natural. You pump a huge amount of energy into a small region, dumping it into various quantum fields. Those fields get excited, they vibrate intensely, and those vibrations manifest as the new particles we detect. Energy converts into field excitations, which are particles.
That makes a lot more sense than particles just magically appearing. But then, what about mass? If particles are just ripples, how do some ripples have mass, like electrons, and others don't, like photons?
The Higgs mechanism. This is where the Higgs field comes in. Remember, mass is really just rest energy, EMC squared. Now, the Higgs field is special. Unlike other fields, its baseline energy state, its vacuum state, isn't zero. Space isn't empty. It's filled with this constant background Higgs field value everywhere.
So empty space isn't really empty.
Not in the QFT view. It's teeming with this invisible Higgs field. And particles acquire mass through their interaction with this background field. You can sort of picture it like moving through treacle or maybe a crowded room. If a field excitation of particle interacts strongly with the Higgs field, it's like it constantly bumps into it, experiences drag or resistance.
Right.
That resistance is its inertia, its mass.
So more interaction, more mass.
Exactly. The top quark interacts very strongly with the Higgs field, so it's incredibly massive. The electron interacts very weakly, so it's very light.
And photons.
Photons and gluons, too, don't interact with the Higgs field at all, so they feel no drag, they're massless, they travel at the speed of light.
And finding the Higgs boson particle in 2012 was basically finding the ripple in the Higgs field itself, confirming the field is real.
That's exactly it. Finding the Higgs boson was finding the excitation of the Higgs field, which confirmed this whole mechanism for how fundamental particles get their mass. A huge triumph for QFT.
Okay, this field perspective is radically different. Let's circle back to that initial question then. How does energy from, all over the universe converge on a point? Given this QFT picture, that idea sounds, well, wrong.
It is fundamentally wrong, yes. Modern physics, especially QFT and relativity, is built on the principle of locality. Things only interact with their immediate surroundings.
Locality, meaning no spooky action at a distance.
Precisely. Influences, forces, energy transfer, it all happens locally. An effect here is caused by something right next to it just a moment before, and that influence propagates outwards, ripple by ripple, never exceeding the speed of light. That's relativistic causality. Nothing jumps across the universe instantly.
And this applies to energy flow too, right? It's not just that the total energy is conserved, but it's conserved locally.
Absolutely. Energy doesn't just vanish here and reappear over there. It has to flow continuously through space. We have mathematical tools like energy density, how much energy per volume, and energy flux, how energy flows across a surface, to track it precisely.
Like the Poynting vector in electromagnetism.
Exactly like that. It shows energy flowing through the electromagnetic field. This framework makes the idea of energy non-locally converging from vast distances onto a single spot completely impossible. Energy has to get there step by step, respecting the speed limit.
So if influences are only local, how do particles interact then? If an electron over here affects an electron over there, but locally, how does the message get across?
Through exchange particles. The force carriers we mentioned earlier, the gauge bosons, they act as messengers. When two charged particles interact, say via the electromagnetic force, they do it by exchanging photons. One particle emits a photon, the other absorbs it. For the weak force, it's W and Z bosons. For the strong force, it's gluons.
And these exchanges are local events.
Strictly local. The emission happens at one point in space-time, the absorption at another. The boson travels between them.
Okay, let's unpack this. Walk me through that classic example. Two electrons repelling each other. What's happening in QFT terms, step by step?
Right. So initially, you have two localized excitations, two ripples in the electron field. They represent our two electrons. Then, at a specific point in space and time, one electron ripple interacts locally with the electromagnetic field. It jiggles the electromagnetic field, creating a ripple in that field, which is a photon. Often, it's a virtual photon, meaning it's short-lived, part of the interaction itself.
And energy and momentum are conserved right there at that spot.
It's perfectly conserved, locally. The electron recoils slightly. The photon carries away some energy and momentum. Then this photon ripple propagates through the electromagnetic field at the speed of light. Eventually, it reaches the location of the second electron ripple, and there's another local interaction. The photon gets absorbed by the second electron ripple. This absorption transfers the photon's energy and momentum to the second electron. The second electron recoils.
And from the outside, we just see the two electrons moving apart, as if pushed by a force.
Exactly. What looks like repulsion at a distance is actually this beautiful, intricate dance of local events. Emission of a field ripple, propagation of that ripple, and absorption of the ripple, all mediated by the fields, all strictly local and causal.
So the energy from the universe isn't converging. The energy is in the fields everywhere as potential, and the convergence is just this local interaction point, this vertex, where ripples meet and exchange energy.
You've got it. The fields provide the stage and the potential, but the action is always local, always mediated. It's a much more dynamic and interconnected picture than point particles in empty space.
But even QFT isn't the final word, is it? You mentioned it breaks down when you try to bring gravity fully into the quantum picture. Those singularities pop back up.
That's right. QFT is what we call an effective theory. It works brilliantly in its domain, at the energy scales we can access. But combine it with general relativity, and the maths gets messy again, particularly at very high energies or small distances, like near singularities. This tells us we need something deeper, a theory of quantum gravity, to unify quantum mechanics and general relativity.
And that's where things get even wilder with ideas like string theory and loop quantum gravity.
That's the frontier. And what's fascinating here is that these two leading candidates take very different routes, but they both point away from the fundamental point particle.
Okay, give us the quick version of string theory.
String theory says the fundamental entities aren't points, but tiny, vibrating one-dimensional loops or segments of string. Incredibly small, like 10 to the minus 35 meters, the Planck length. Different particles, electrons, quarks, photons, even the graviton, the particle of gravity, are just different vibrational modes of these strings, different notes the string can play.
And because they're strings, not points, they have a tiny size.
Exactly. They have extension. And that tiny bit of fuzziness, that finite size, is enough to smear out the interactions and potentially resolve those problematic infinities and singularities. It also, intriguingly, seems to require extra spatial dimensions, maybe 6 or 7 more, curled up incredibly small.
Wow. Okay, and loop quantum gravity, how does that approach it?
LQG takes a completely different tack. It doesn't assume a background spacetime for strings to vibrate in. Instead, it quantizes spacetime itself. It suggests that space and time aren't smooth and continuous, but fundamentally discrete, granular, made of indivisible quantum chunks, or atoms, of space and volume, again at the Planck scale.
Like pixels on a screen.
Sort of, yeah. Spacetime itself becomes this dynamic network, a spin network. Because there's a minimum possible volume, you simply can't compress anything down to an infinitely small point. Infinite density becomes impossible. This could resolve singularities naturally. The Big Bang might not have started from an infinite point, but maybe from a big bounce, a phase of maximum but finite density.
So we have strings vibrating in extra dimensions versus a pixelated, quantized space-time fabric. Very different ideas.
Very different mathematical frameworks and pictures of reality, yes.
Yeah.
String theory needs extra dimensions and supersymmetry, usually. LQG works in 3+1 dimensions and focuses on quantizing geometry itself. They make different predictions, though testing them is incredibly difficult right now.
But what's the common ground? What's the big takeaway from both?
The stunning convergence is this. Both leading candidates for a fundamental theory strongly suggest that the mathematical concept of an infinitely small point has no physical reality. Whether it's the minimum length of a string or the minimum quantum of volume, both theories impose a fundamental limit, a finite resolution, to reality at the Planck scale. The smooth, continuous world we see is just an approximation, merging at larger scales from this deeper, fundamentally granular or stringy reality. The point particle seems doomed.
What an absolutely incredible journey. We started with that intuitive, almost common sense idea of a point particle, found it riddled with paradoxes, moved to this universe of vibrant quantum fields where particles are just ripples, learned that interactions are strictly local exchanges, not spooky action at a distance, and now we find ourselves at the frontier where reality itself might be fundamentally grainy or stringy with no room for infinite points.
That's a great summary. If you take away a few key things, let it be these. Fields are the fundamental reality. Particles are excitations, ripples, and those fields. Mass comes from interaction with the Higgs field, and absolutely crucial, all interactions are local and mediated by exchanged particles. That idea of energy just converging non-locally from everywhere onto a point, that's definitively ruled out by everything we know about physics.
So here's the final thought to leave you with. If the very fabric of reality isn't smooth, if it has a fundamental pixel size or is made of tiny strings, what does that truly imply? How does that change our understanding of space, of continuity, maybe even of consciousness, and our own place within this deeply interconnected, subtly buzzing universe? Something to ponder.